This is our first lecture for the topic motion in a plane. So students, they must be aware of the motion in a straight line. That is when we are talking in 1D. So what we say is in a, in the motion in one dimensions, this is a straight line. And suppose the initial particle's initial position is this. It can either move here to this position, it can either move here to this position, or it can come back again to this position. But whatever the particle does, it always remains on that straight line. That is said to be the motion in a straight line, and this is 1D. And when we are talking about two dimensions, we say we are basically talking about the motion of the particle in a plane. So this plane is formed by this two dimensions or this axis. This is the x-axis and this is the y-axis. This is the x-axis and this is the y-axis, and our particle can either be here, it can either be here, or even this is said to be the origin. These axes, they can be extended to these left and right also, and the particle can either be here, but it has to be in on this plane only. It cannot be coming out of the plane. So this is the introduction to the motion in a straight line and a motion in a plane. Now, so this is our motion in a plane, and our first topic today would be scalars versus vectors. So first we'll learn about scalars. Scalars are the quantities that have only the magnitude and no direction is involved. So only magnitude is needed to specify them, and no direction is needed to specify them. Some of the examples that we can talk about here is for the scalars is distance, mass, temperature, and time. For example, we say we talk about distance as if it's 5 meters. So we are not talking about any direction. 5 meters is in this direction. It can be anywhere. And if we talk about mass, as the mass is 5 kg. So mass doesn't have any direction. Also time, 5 seconds, it doesn't have any direction. Like there is no logic behind talking about direction of the time. So these are the quantities that actually have no relation with any kind of direction. So these are the scalar quantities. Now they can either be dimensionless if it is the constant, or they can also have the particular kind of units as we just discussed. Also, these one important thing is that in the case of unit operations, we talk about the rules of addition, subtraction, multiplication, and division. They are very similar to the ordinary algebra rules. For example, first let's write this. The rules are similar to the ordinary algebra rules. For example, if we take a rectangle, let's draw a rectangle. This is the breadth of the rectangle and this is the length of the rectangle. And if we talk about the area is simply written as length and breadth. As we have discussed, the distance is a scalar quantity. So here length and breadth are also the scalar quantities. Let's take length as 5 meters and breadth as 2 meters. So the answer would be 10 meters square. So the result here shows that the whatever unit operations that we do on the scalars, the result that comes out will also be in the form of a scalar. Here 10 meters square, that is the area, is also a scalar quantity because it also does not have any direction. But as we see simply here that the units of the length and breadth are not the same as the units of area. The units are also multiplied together to give meter square. So this is the thing that we need to remember. And another example that we can talk about here is when we are given mass and volume, we can calculate the density. Density is mass by volume. Mass and volume both are the scalar quantities, and therefore density also comes out to be a scalar. And the units also the units are they can be adjusted, and we can find out the density units to be, suppose the mass is given in kg and volume is in meter cube. So the units of density will be kg per meter cube. But again, the result is always a scalar. Density is also a scalar quantity. It does not have any direction. Now coming to the vectors. Vectors are the quantities that have to be specified by both the magnitude and the direction. That is, even if it does not specify the direction, the information will remain incomplete. For example, if we say displacement, the particle has gone from some initial position to some final position, and this is the displacement. But the reader will want to know that the displacement is in which direction. If we talk about the speed, another example of a vector quantity is velocity. So if we say that the velocity of a bike is, let's suppose, 10 kilometers per hour. So that will, we will want to know that in which direction the bike is moving. So it can either be left or it can either be right. So the velocity also needs a direction to be specified. Another examples include acceleration, force, etc. Now we will talk about how the represent the vectors in most of the textbooks that we see. In most of the textbooks, we will see that any vector, suppose v, it is written in the bolded form. Like v will be written and it will be bolded. And also sometimes they use a normal v in italics and they put a bar or this is a bar or this is an arrow. They put a bar or an arrow over that quantity to denote that this is a vector quantity. So while writing, everybody, we should always remember to use a bar if we are working with the vector quantities. Otherwise, we'll end up in the confusion with the vectors and the scalars. And a magnitude is written, that is the length of any vector, that is written as mod of v. So this is the magnitude, or we can say the absolute value of that vector. We'll see what all this means a bit. So another difference between the vectors and the scalars is that they do not follow the ordinary algebra rules as the scalars do. So what they do is instead they obey different type of rules of addition, subtraction, and multiplication, as we'll discuss in the subsequent classes. So some of the rules that we'll discuss is the triangular law of addition or the parallelogram law of addition to add the two vectors. They cannot be simply added by their magnitudes, because they also have a direction and we need to take care of that direction also. First, let us see how is a quantity written in a vector form. And for this, we will need to get aware of the concept of position vector and the displacement vector. So to understand this, we should first have a 2D plane for the better understanding. So this is the x-axis, this is the y-axis, and suppose we have a point, or we can say we have a particle at some point P. It is right what everything all this is. This is the x-axis, this is the y-axis, this is some point P, and this is some another point P dash. This is the origin that is also need to be specified always in the 2D plane. So this vector OP is said to be the position vector. So let's suppose a particle is sitting here at P. So OP will be its position vector. And suppose another particle is sitting at P dash. So OP dash will be the position vector for that particle. So here we can say that position vector, here are OP for the particle P and OP dash for P dash. And displacement vector concept comes into play when we say that the particle is initially at some point at P, and then it moves away from that point and reaches P dash, which is the final position. So then the vector, that is the displacement vector that would be said as pp dash. P would be written first because that's the initial position of that particle. And here we will say that p dash is a displacement vector. So here one important thing to note is that we have simply drawn pp dash as a displacement vector. But displacement vector is always a straight line which is joining the initial and the final position. And so it does not depend upon the actual path which is taken by the object. For example, if we say that this is the point P and this is some another point P dash and the particle starts from P and it moves to P dash via this path. Or we see that this particle starts at P and it moves till P dash via this path. This is where arbitrary path. It can be anything. Or this path. But in all the cases, this PP dash is a displacement vector. This will always be a straight line which is just joining P to P dash. So the displacement vector does not depend upon the path. That was the students, they must have been told about the difference between the distance and the displacement in a similar way, because we say that the length of the path that any particle travels, that is the distance that it covers, and displacement is always the distance between the initial and the final positions. So here the same here also the case is same. The displacement vector is simply a straight line. Now we'll get to another topic, that's the resolution of vectors. So just now we have seen that how a vector is represented on a 2D plane. How we can draw its position vector, and if it's changing its position, how we want to draw its displacement vector. Now we want to see that how to write a vector mathematically. That is, we always cannot draw a vector in the complex situations in a graphical plane, in a 2D plane, and so we can simply write it in a mathematical form. First, let's get aware of a very important rule of algebra, that is, in n dimensions, any vector can be written as a linear combination of two basis vectors. That is, if in simple terms, if we want to write it as this is a very important rule of algebra, and we'll see what this n dimension means. Like if we are talking about the 2D only, two dimensions, then we say that any vector A, it can be written as a linear combination of two basis vectors. So here our basis vectors are A and B, and our final resultant vector is A, and X and Y, they are just the numbers. And this thing is said to be the linear combination. So the basis vectors actually mean that they are the standard vectors in terms of which any other vector can be written in any dimensions. We are studying about the two-dimensional case, that is in a plane. So our system, we take the orthogonal unit vectors as our basis vectors. That is, let me write this. First important keyword here is orthogonal. How to decide the basis vectors? So first thing here is orthogonal. That is, the vectors that we are basis vectors that we are taking, they must be 90 degree to each other. And second is unit vectors. Unit vector simply means that their magnitude is 1. The magnitude of that vector v should be equal to 1. So orthogonal unit vectors, they are taken as a basis vectors. In our case, in 2D, this is the x-axis and this is the y-axis. In our case, our unit vectors are I cap towards the x-axis and j cap towards this cap thing. This cap simply denotes that they are the unit vectors, that their magnitude is unity. So do not have to be confused with this. And I and j, they are simply the vectors of unit magnitude, and they are at 90 degree to each other. So both these conditions, they are satisfied, and here we take I and j as our basis vectors. Now I would like to emphasize here that a vector can be resolved into any two other vectors, a and b. That as here we have written a and b. We have chosen the unit vectors as I and j because it is convenient for the mathematical calculations, as I and j, they point in the same direction as our axis of the rectangular coordinate system. So it is only because our convenient and the simplicity of I and j that we have chosen these. There is no constraint that we have always to choose I and j. They can be any a and b. So mathematically, if using I and j, if we want to write any vector, we can simply say that any vector a, this is a vector, it can be written some number, that is ax times of I cap, and some number ay times of j cap. So here I and j, they are the vectors, and ax and ay, they are the numbers. So simply we can write any vector in this mathematical form. Now we will go on to look how to represent the vectors. So let's take a new page. Representation of vectors in different coordinates. That is, if we are given a vector, the same vector, it can be represented in a different ways, giving the different information. And we'll come to this. Let's first see what are these two coordinates. The first one is the Cartesian or the rectangular coordinates, and the second one is the polar coordinates. So I would need a 2D plane to explain this. So let's draw a plane first. This is the x-axis. This is the y-axis. This is the origin. And here, let's suppose there is a point. So this is the x-axis. This is our origin. This is our y-axis. And this is some point P. So as we just discussed, that A vector, it can be written as AXI plus AYJ. That simply means where to get these AX and AY from, because I and J we know. Sorry, these are not the vector symbol, but this is only to denote the magnitude. Here I and J are known because I and J, I will be pointing towards the x direction, and Y and J is pointing towards the y-axis, x-axis and y-axis. But AX and AY are not known. So let me first tell you what these AX and AY, how can they be calculated. So suppose this is a vector A, OP vector is a vector A. To calculate AX, what we do, we simply put a line which is perpendicular from this point P to the x-axis. So this is the perpendicular line. And similarly, we will also put a line which is perpendicular from this point P to the y-axis. This is also a perpendicular line. So this distance is AX, and this distance is AY because it's in the y-axis. So the thing, this concept is known as a resolution of vectors because we have discussed that any vector can be resolved into two other vectors. So here we have resolved it into two components, that is AX and AY, which are in the x and the y axis, which are in the x and the y direction respectively. So here AX and AY. So, so if we want to specify a vector, and if we simply write a vector in this way, we can know that this is given as AX and AY, or we can also write, if we say that a particle's position is AX, comma, AY, we can draw this kind of vector A. We can use this information to find the vector OP. We can simply plot this AX and AY points on this 2D plane, and we can join the O and the point P with the help of a position vector, and so we will get this vector OP. So this is the similar. This is the case for the Cartesian or the rectangular coordinates. When we specify any vector using its components ax and ay, then this is the Cartesian or the rectangular coordinate system. When if we are talking about there is another case in the 2D plane. Suppose we are aware of the length or the magnitude of this vector OP. Let's suppose it's r. This is simply a number or a length. This is not a vector. It's simply the length or this OP. And there is some direction. There must be some direction that this vector makes with the x-axis that is known as theta. This theta, remember that this theta always has to be the angle between this vector and the x-axis and not the y-axis because this theta is as standard taken with respect to x-axis. So when we specify any vector in terms of r and theta, then we say that we are specifying the vector in the polar coordinates, that is r and theta. That means we need two pieces of information for specifying a vector. If we talk about the Cartesian coordinates, that two pieces of information here are ax and ay. And if we talk about the polar coordinates, that two pieces of information are r and theta, that is the magnitude of that vector and the angle that it makes with the x-axis, theta. If these two are specified, we can specify the vector. So these are the two ways to specify any vector. Now, uh, we can also find out the relation between these four quantities, that is ax, ay, and r and theta. These four quantities, they are all related to each other because they all specify the same vector. So we can find out the relations between these quantities. So we can say here that if r is the magnitude of that vector, we can say using the simple trigonometry that if this is r, this is ax, this is ay. These three are the lengths. So this r cos theta will be ax. Simply we can simply write it using trigonometric rules. Ax is simply r cos of theta and ay is this is cos, this is sine. So this will be r sine of theta. So here ax and ay. And if we know the Pythagoras theorem, so we can also say that this is ay same. So this can be this is the length ay, and here it can be written as ax. And if we apply Pythagoras theorem in this triangle, we can simply say r square is equal to ax square plus ay square. And again, if we use the tan theta property, tan theta will be equal to, in the same triangle, tan theta will be ay by ax. So these four relations, they are basically the relations between these four quantities. These four relations are very important relations. These all must be remembered, or even if not remembered, you all must have now understood the idea that how to calculate them. Using simple trigonometry and the Pythagoras theorem, we can calculate these. So if we want to convert, now let's come to the conversion using the conversion from one coordinate to the other coordinate. The first is if magnitude, that is r, and angle theta is given, and we want to calculate the ax and ay, that is it, the components of the vector, then what should we do? So simply we have seen these relations just now. We know r and theta, that is the information that is given to us is r comma theta, and we want to calculate ax and ay. So from that previous diagram, we can simply say ax is equal to r cos theta and ay is equal to r sin theta. And conversely, if components are given, that is the information that is given to us is ax, comma, ay, and we want to calculate r and theta. So that also we have seen that r will be under root of, using the Pythagoras theorem, r square is equals to ax square plus ay square can be written as this. We can calculate the r, and for theta we will use the tangent property. Tan theta is equal to ay by ax. So these four relations, they can be used for the conversion purpose, and we'll also solve one practice problem related to this to avoid any confusion. Now everything that we discussed, it was for 2D. Now the same concepts, they can be applied for 3 dimensions as well, where we take our x, y, and z and our I, j, k as our basis vectors. So I can, this is our x-axis for 3 dimensions, y-axis, and the third axis, that is the z-axis, that is taken out of the plane of paper or of the computer screen or inside the plane. Generally, it is taken outside for the positive direction. And for our unit vectors, let's say this is the I cap, I label them. This is the x-axis, this is the y-axis, this is the z-axis, this is the basis vector, that is the unit vector I cap, this is j cap, and here it is taken as k cap. This is the origin. And so these vectors, they must be, and if we take any point P, suppose, that is at this point will be in 3D space. So it's not compulsory. It's that this will lie on that 2D plane. It can be somewhere out of the plane of the screen. But to denote this, I will let's suppose. But to denote this, I'll write it in this form. Suppose this is the point P. So this line, it will make some angle with the x-axis. So this angle shall be called as alpha. This line, this position vector of that point P will make some angle with the y-axis, that will be called as beta. And this line will also make some angle with the z-axis. This angle will be called as gamma. So here what we have seen, that we have in 3D, we will have x, y, and z-axis. In the case of unit vectors, we will have I cap, j cap, and k cap as the unit vectors, and the corresponding angle that any point P or a position vector OP will make with the corresponding axis. That OP will make x-axis will make an angle of alpha with the x-axis, make an angle of beta with the y-axis, and gamma with the z-axis. So these are the angles. So the results, they can be extended to the 3 dimension system also, the 3D space, and we can write the magnitude. Suppose if we want to write this vector in, we will write A, this is a vector, it will be AX, I cap, AY, J cap, AZ, K cap. This is the way how to write a vector in 3D mathematically. Then if we want to calculate the magnitude of A can be written as this, or this can be said as R that we just discussed. That was equal to AX square, AY square, AZ square. And for the angles, we can take, like here we have taken R cos of theta for AX. So here we can take AX, A or R cos of alpha, AY R cos of beta, and AZ R cos of gamma. So this is for the 3-dimensional case. Now we'll also practice some problems Let's see the first question. Here the problem says that if I'm sorry, this is a plane, and suppose our particle is initially at point A, it then moves to some other point B, and again it comes to some third point C. So the path of that particle would be this, A to B, and then B to C. And the question says find out displacement vector for the above particle where A is defined as 2i plus ij. This is the position vector of that point A. Sorry, let us first write this. Denote it as a vector. B is 4i cap plus 6j cap, and C, it is minus of 2i cap minus of 7j cap. Now we want to calculate the displacement vector over here. So as we are aware of that difference between the distance and the displacement, some of the students, they might think that the particle will first go from A to B. So we'll calculate the displacement vector from A to B, that is d minus A, vector. And then in the second step, we will calculate the displacement vector from B to C. So for some students, what they may do is first they will calculate for A to B, and then they will calculate for B to C, and then they might add the two results, or they may subtract the two results. But this is not the way to do it, because we are not interested in the distance the particle is covering, but we are basically we want a displacement vector, and we all are aware that it does not depend upon the path. That is, we are only interested in the initial A and the final C positions. So we can directly calculate the displacement vector. Let's suppose the displacement vector is D, as that is the final position is C and the initial position is A. So that will be C minus A. That will be C minus A. So here the result will be, so this is the displacement vector. Now coming to the second problem, that is for the conversion. This is the conversion from one coordinate to the other coordinate system that we discussed to represent any of our vectors. So what we are given is the Cartesian form, minus root 3 to comma 1. We have to convert it to polar form, that is r comma theta. So what we are given, that is x comma y, or we can say ax comma ay as per our formula, and we want to find r comma theta. So what we discussed was, according to the Pythagoras theorem, r, that is the magnitude of any vector, that is written as under root of ax square plus ay square, that can be written as minus root 3 whole square plus 1, that is basically 3 plus 1 4, and its under root is 2. So we will simply get the r, that is the magnitude of that vector, and now we want to calculate theta. And we know the derived formula, that is tan theta here is ay by ax. Ay is 1, ax is minus root 3. So, and if we want theta, we have to do tan inverse of theta will be tan inverse of minus 1 by root 3. So here minus may pose some kind of confusion for some students. So the best technique that I use to find out theta is always using the quadrant frame. That is we know that there are 4 quadrants in a 2D plane. It's the first, second, third, and fourth. So what we can do is we can approximately locate the particle. That is, if we know that x is negative, that is x will be negative. So x will be in this part of the axis, and y is positive. So y will be here. So the particle simply means that it is somewhere in the x quadrant only. We do not need the exact location of the particle, but we can only look at the signs of ax and ay, and we can locate it approximately. So that means the particle is in the second quadrant, and we have already calculated r, that is 2. Is already 2, and now we want this angle theta. So the best way is we can first calculate this angle, let it be theta prime. So this angle with this axis, with the y-axis, that's theta prime. So what we can say is theta prime will be tan inverse mod of minus 1 by, that is we can neglect the sign and we can write 1 upon root 3, which is 30 degrees, or in radians we can write it as pi by 6. So this is we have neglected the negative sign, and we have now calculated tan inverse, which is 30 degrees. So this theta prime is actually this angle. It is drawn over here, but we want to calculate theta actual. It is complete. So simply theta actual, it can be written as we can see, it is in the second quadrant, so it will be 90 degrees plus theta prime, which is 30 degrees. So it is 120 degree, or in radians we want to write, it can be 2 pi by 3. Now suppose for some any arbitrary another particle, if the particle's position is this, that is in the third quadrant, we can simply calculate r using this formula. R can be known, but now we want this complete angle. So what we'll do is we'll neglect the negative sign, and we'll calculate tan theta, the tan inverse of ax by ay by ax. We will calculate tan theta of ay by ax, and we'll take the mod of this ay by ax. That is, we'll not take the negative sign into consideration. We'll calculate theta, and for the third quadrant case. So we'll write this. If for the third quadrant, if the particle lies in the third quadrant, we simply add 180 degree plus theta. And similarly, if the particle lies in this fourth quadrant, we need to add 270 degree plus, this is theta prime, plus theta prime. Now, here one thing to notice is that for the fourth quadrant case, we are not subtracting, because this angle, this theta, we are considering this theta prime. We are not considering this theta prime, because we must be aware that this theta in our convention, it is taken always in the anti-clockwise direction. That is, this is the direction of theta. That will always go from this in this direction. So always we will get this theta. So from this axis we will get this theta prime only. So we need to add 270 to get the actual theta. So this is how I prefer doing my problems to avoid any kind of confusion, and it may also seem suitable for many of you to do the same. Now conversely, if we will do the converse for this case, here we want to convert, as we know that this is given in radians, so this cannot be ax or ay, it is obviously r comma theta, that is the angle, and we want ax and ay. So this conversion does not involve any kind of trick or any kind of confusion. It's simple. We simply have to put the corresponding formula. So as I discussed, ax is r cos of theta, so r here 2 cos of 5 pi by 4, and the value comes out to be minus root 2. Similarly, ay will be r sin theta, which is 2 sin pi by 5 pi by 4, and here also on calculating this, we will get minus root 2. So simply x comma y or ax comma ay it is minus root 2, minus root 2. Then I would like to give one homework problem to everybody and we'll discuss it in the next lecture. This topic of vector addition we have not discussed so far, but I want everybody to first try this and think about this problem. And then anyways, we'll discuss it in the next lecture and we'll see if this equality holds or not. That is just the associative law. We'll end the class here and we'll start with the equality of vectors in the next lecture. Thank you.